If you ask anyone what color the sky is, they will tell you it is blue. Many grew up hearing the popular explanation that the sky is simply a giant mirror, reflecting the blue water of Earth's oceans. The real answer actually starts 93 million miles away. When we look at the sun, the light it emits appears white. In reality, that white light is a tightly packed bundle containing every color of the rainbow. We reveal these hidden colors by passing a beam of sunlight through a glass prism. The angled glass splits the white light into individual components. Every individual color in that spectrum behaves as a light wave with its own specific, measurable physical length. To understand why the sky looks the way it does, we have to stop treating it like a painted canvas and start tracking how those specific color waves travel from the sun all the way down to the ground. When light waves enter our atmosphere, they follow a strict physical rule. Long waves travel in straight lines, while short waves get scattered out of their paths. This diagram shows Rayleigh scattering. The math dictates that a light wave scattering is inversely proportional to its length. As a wave gets shorter, its scattering intensity exponentially explodes. Here, blue waves are short, but violet waves are the absolute shortest. If we run the sunlight through that scattering equation, the numbers are clear. The atmosphere is scattering significantly more violet light than blue light. If the strict laws of physics dictate that the air above us is saturated with scattered violet light, why do we look up and see a completely blue sky? The space between the sun and the ground is not empty. Earth is wrapped in a dense layer of gas, primarily nitrogen and oxygen molecules, that acts as a massive obstacle course. This diagram shows how the longest waves interact with that gas. Reds and yellows easily slide right past the trainee molecules, but the short, choppy blue and violet waves violently crash into the gas, fracturing and ricocheting outward in random directions. Trillions of these short waves are colliding and bouncing around every single second in the air above us. The sky itself has no inherent pigment. It is simply a transparent container illuminated by these trapped, ricocheting short waves of light. We still have our paradox. The atmosphere is filled with a chaotic mix of light, and the physics prove the mix is heavily biased toward violet. Yet the violet is missing. Part of the answer lies with the star itself. The sun's solar output naturally produces slightly less violet light than blue light to begin with. The real explanation isn't found in the air, but inside the human retina. Our eyes process light using specialized photoreceptor cells called cones. This chart shows human visual sensitivity across the light spectrum. Our retinal cones are highly tuned to detect blue light, but the sensitivity drops drastically near the violet section. We are virtually blind to the shortest wavelengths. The sky above us is actually a vibrant blend of violet and blue. Our brains act as a biological filter, editing out the violet and defaulting to the blue we actually have the physical hardware to see. That biological illusion holds up perfectly all day. Then evening arrives, and the blue gives way to deep reds and vibrant orangers. This diagram shows the changing variable, distance. When the sun drops to the horizon, its light no longer takes a short vertical path. It has to push horizontally through a drastically thicker slice of the atmosphere to reach you. Because of that long journey, the short blue and violet waves scatter over and over again until they completely disperse, well before they ever reach your eyes. A red sunset is an exercise in the survival of the fittest light waves. Only the longest red and orange waves can endure the marathon through the thickest part of our air. To see exactly how rigid these physics rules really are, we can look at a different planet entirely. Mars has an atmosphere, but with a completely different set of ingredients. Instead of thick nitrogen and oxygen, Mars has a very thin atmosphere packed with fine suspended dust particles. These tiny particles scatter light in the exact opposite manner of Earth's gas molecules. Because of this dust, the Martian sky is orange during the day. But when the sun sets and the light travels through the thickest part of that dusty atmosphere, the evening sky takes on a striking blue-gray tone. The colors of our world are not absolute truths painted onto the sky. They are the result of a delicate, invisible collaboration between the fire of the sun, the specific gases blanketing our planet, and the unique biological wiring of the human mind.